Oh, welcome and thank you for joining. In this lesson, we'll go over one of the most mysterious, most beautiful, most elegant proofs in vectors, the dot product. In order to best understand this, let's revisit all the things we've learned about vectors so far. Recall that we started off with geometric vectors, which were vectors that looked just like A and B that I've drawn here. And we describe the size or the magnitude of a vector by simply using the length of the vector. And when it came to direction, we were able to describe the direction of a vector only in relation to other vectors that lied on the same plane. So we placed them tail to tail, and we said that vector A makes this specific angle with vector B. We learn how to add two vectors by using two or more vectors, by the way, by using triangle and parallelogram law. Now for triangle law, we place them head to tail. So vector A plus vector B placed head to tail will give A plus B. So the vector that started with the tail on the first vector in the addition and the head in the second vector in the addition. We learn how to subtract two vectors by simply placing head to tail the vector A, which is the first vector in the subtraction, and we place vector negative b at the head of vector A, and then we found the sum A plus negative b, or the difference between A and B. We learn how to multiply a geometric vector by a scalar. So if this is vector B, vector 2b will be twice as long following the exact same direction. And if this was a vector B, then vector negative 3b will be 3 times as long and going in the opposite direction of vector B. We also learn how to add two geometric vectors by using the parallelogram law. This is the tail-to-tail addition. And we place the two vectors tail to tail, and the sum vector will be the diagonal that comes or has the tail at the common tail of the two vectors that are being added and the head in the opposite vertex. When we subtract two vectors in a parallelogram rule, we place vectors A and negative b tail to tail, and then we find the sum of A plus negative b, which is simply the difference A minus b. Next, we moved algebraic vectors on the Cartesian plane. So an algebraic vector will practically look like this. Anywhere this vector goes is an algebraic vector. Now, for this, we needed to know the coordinates of the tail and the head, and then to make things easier to communicate, we said, if you move this vector with the tail at 0, 0, you will automatically know that the tail is 0, 0. We call this a position vector when the tail was at 0, 0. And all you need to know to determine the location and the size of a vector was the coordinates of the head. We learned how to add algebraic vectors, and that was fairly easy if you recall. So for both vectors 2D and 3D, we follow the same strategy. So to add, we added the respective coordinates, so x's together, y's together, and z's together in 3D. And to subtract vectors, we subtracted the respective x coordinates together, y coordinates, and the z coordinates. And obviously in subtraction, if you're subtracting OB from OA, that means that you are subtracting x at B from x of A. Same thing, y of B minus y of A, z of B minus z of from z of A. We also learned how to multiply a vector by a number. So we said that if a number multiplies a vector with coordinates x and y, then the multiplication by a scalar, that's exactly what this is called, will create a vector with coordinates kx and ky. And if we were in 3D again, we add the third coordinate kz. So for both geometric and algebraic vectors, we've learned how to add them together, how to subtract them together, and how to multiply a vector by a number. Now the question becomes, can we multiply a vector by another vector? We've never done that, right? So obviously the answer to this is yes, but before we go over the process and explaining how this works, I want you to think about it. If you had two vectors, OA and OB, and you were to multiply them, how would you multiply two vectors? Recall how we added them. So when we added vectors, we added their coordinates, respective coordinates. When we subtracted the respective coordinates. How about multiplying them? Obviously, it has something to do with the coordinates, and it has something to do with multiplication. So to multiply two vectors when in algebraic form, what we do is we multiply the respective coordinates. That's exactly what we do with vectors when they're given in algebraic form, or as we call them, in standard form. So if vector OA in 2D has the coordinates xa, ya, and vector OB has coordinates xb and yb, then the product OA times AB would be x of A times x of B plus y at A times y at B. And in 3D, we have to take care of the z coordinates as well. So we add the product ZA, ZB. The formula for the dot product, that's exactly what we call it, because in vectors can be multiplied in two different ways. And this form of multiplication is the first form of multiplication we look at. But there is another way we can multiply two vectors, and because there are two different ways to distinguish them from one another, we use different symbols in multiplication. So when you think about it, there are two ways we write multiplication, either with a dot or with a cross. So for example, we can say 2 times 3 or 2 times 3 this way. And to distinguish the two different ways of multiplying two vectors, we use the dot for the proof that we are going over today, and we use the cross for the what we call the cross multiplication, as a matter of fact, which we will discuss in the future lessons. So dot product, and that's exactly what we call it based on the symbol that we use to indicate the multiplication or describe the multiplication, states that two algebraic vectors A dot B would equal the magnitude of A, magnitude of B, cosine of theta. Now I want you to think for a second. The A dot B is when two vectors are multiplied by using their coordinates. So that means that these two vectors must be in algebraic form. And when you look at the right side, you see that magnitude of A, that's a number, magnitude of B is a number, cosine of theta, where theta is the angle between two vectors when placed tail to tail, is also a number. So the other side will be the product of three numbers, which means that the right side will be just a number, or should we say a scalar? So I'm going to say that the dot product of two algebraic vectors will actually equal another number or a scalar, and this is why we call the dot product also a scalar product. Now, remember that there is a difference between saying scalar product and scalar multiple. A scalar multiple, and I want to explain this now before it's too late, and we mix them up. A scalar multiple of a vector is when you multiply a vector by a scalar. So you can make it longer, shorter, go opposite or same direction. So, and in a scalar multiple, we have the product of k, which is a scalar with a vector, producing another vector. Whereas in a scalar product, which is the same thing as if saying the dot product, the product of two vectors would be equal to another number. So here we multiply two vectors that give a number, and here we multiply a vector by a number that give another vector. So how are these two sides of the equation connected? And as you can see here, the right side of the equation represents quantities that we can easily determine or evaluate in geometric vectors as well. And that's why we call this a connection, or we say that the dot product connects the algebraic with geometric multiplication of two vectors. But how are these two sides connected to each other? Where do they come from? And this is what we are going to explain right now. So suppose we have two vectors OA and OB. Now vector OA will have the coordinates XA, YA. OB has coordinates XB and YB. Now we'll connect the head of vector A with the head of vector B, and we will form a new vector, AB. As you can see, vectors OA, AB, OB are in a triangle, so they must be connected somehow in some ways by the triangle law of either addition or subtraction. We don't know. So let's take a closer look at it. So when we add two vectors, we place two vectors head to tail. So I want you to locate two vectors that are placed head to tail. You probably noticed that vectors OA and AB are placed head to tail, and vector OB has the tail at OA and the head at AB, which means that the vector OB is equal to the sum of vectors AB and OA. Now, for simplicity, we are going to give a new name to vectors OA and OB, so we'll call vector OA vector A, lowercase a, and vector OB, lowercase b. So in simpler words, then we'll say that vector B equals vector AB plus vector OA, or vector A. So we'll express vector AB in terms of B and A, and that means that vector AB is, as a matter of fact, equal to B minus A. You can see that, right? Because all we're doing here is isolating AB, which means A is going to the other side. So, surprise, surprise, what we have figured out so far is that this vector AB here is basically vector B minus A. Now, let's talk magnitudes. The magnitude of vector A will be magnitude of A, so absolute value of vector A here. And magnitude of vector B will be this. Magnitude of vector B minus A will be described by just use the absolute values. Now, remember that when we find the magnitude or the absolute value of a number, for example, if we have 3 minus 2, the absolute value of 3 minus 2 is absolute value of 1, that's 1. If we have 2 minus 3, so the absolute value of 2 minus 3 is absolute value of negative 1, that's 1. So if we switch these two numbers around, we still get the same answer. So what we are going to do in this case is, instead of writing B minus A, we'll rewrite this as A minus B. Oops, that was a little bit too much. So vector AB is, or has a magnitude of A minus B in absolute value. So another thing that we want to look into is the coordinates of vector AB, because we have expressed OA and OB using the coordinates. And we want to do the same thing for vector AB. Remember, when we determine the coordinates of a vector by using the coordinates of the head and the tail, we always go tail minus head. So for vector AB, we're going to have x at B minus x at A, that's the x coordinate, and the y coordinate will be y of B minus y of A. So as you can see now, for this triangle, we have the vectors connected to each other by this relationship. We have their magnitudes connected to each other, and we have the coordinates of each vector. Remember, 0 is 0, 0, 0, right? Like point O. So we have the vectors sort of in algebraic form. So we have their coordinates, and we have all the information we need about them as geometric vectors. Now, the angle made between vectors OA and OB will be this angle theta right here, at where the tails are connected to each other. And that's exactly what we'll call it for now, angle theta. Now, what we see is a triangle with lengths AB and A minus B, and this angle theta. We want to connect them. And there is one very popular formula in trigonometry that can connect these three sides and the angle in here together, and that is the cosine law. So just to refresh your memory, the cosine law is like the Pythagorean theorem for non-right angle triangle. So c squared equals a squared plus b squared minus 2ab cosine of angle C. So we'll use this formula here. So if we use this formula, it means that the magnitude of A minus B squared would equal the magnitude of a squared plus the magnitude of b squared minus 2 times the magnitude of a times the magnitude of b. And then multiplied by the cosine of theta, which is the angle across from vector AB. So now we're thinking, how do we find the length of a minus b squared? Well, we do know the coordinates of the vector AB. So in order to find the magnitude of vector AB, what we do is Pythagorean theorem. It's that simple Pythagorean theorem. For example, remember, if you have a vector in here on the Cartesian plane, you want to find the length of it, that would be equal to x squared plus y squared, and then square root it for this length. So we're going to say that a minus b, magnitude of a minus b, would equal the square root of xb minus xa squared plus yb minus ya squared. And this would be the magnitude of a minus b. And we bring this to the power of 2 because we have the magnitude of a minus b squared. So that would equal the magnitude of a squared. As you can see here, magnitude of a is defined by the coordinates of it, xa squared plus ya squared. So xa squared plus ya squared, square rooted. And because we have the magnitude of a squared, this must be brought to the power of 2. Next, we have b squared. So for b, we have coordinates xb, yb, which means that here we have the square root of xb squared plus yb squared, and that brought to the power of 2. And then next we have 2 times magnitude of a, magnitude of b, cosine theta. So let's write that down. I will have to actually readjust the space in here because it seems that we need more room. Okay. So here we go again. We have minus, and then 2 magnitude of a, which is the square root of xa squared plus ya squared, multiplied by magnitude of b, which is square root of xb squared plus yb squared, and multiplied by the cosine of angle theta. So next, we are going to take care of these squares and the square roots because it makes no sense now to write so much when we know that they will simplify. So what we have now is xb minus xa squared plus yb minus ya squared equals, so again, the power and the square root simplify, right? And then equals xa squared plus ya squared. And then plus xb squared plus yb squared. And then the rest of the expression is as is. So we're going to have here 2. And I will rewrite the exact same expression as is. I'm not making any changes at this point. So I'll copy and paste that. That's faster. So double of magnitude of a, magnitude of b, cosine theta. Now let the party begin. We are going to perform some algebraic simplifications in here. Very straightforward, but quite a lot of them. So which means that we need to be very careful when we expand. So xb minus xa squared, that's a binomial. A minus b squared, remember the formula a squared minus 2ab plus b squared. We want to do this fast, right? So which means that we have x at b to the power of 2 minus 2 times the product xb xa plus xa to the power of 2 plus here. Now we have yb minus ya, so that will give yb squared minus 2yb ya plus ya squared equals. Now, on the other side, we have the exact same thing we had before. We're not making much changes in there. So we have xa squared plus ya squared plus xb squared. Let's make sure that we have enough room for this. Not yet. Okay. So look at what we have created now. We have the expanded form. We have the expanded form of the left side, and we have the right side in the most simplified form possible. And now we'll try to do some simplifications. So I'll bring your attention here to xb squared, and I will highlight this as a matter of fact. So here is xb squared. You see that on the other side, we also have xb squared right here. So the two of them will simplify. How? Because if you take this to the other side, they will subtract each other. Next, we have xa squared on the left, xa squared on the right. That is gone. And now we have yb squared on the left, yb squared on the right. Next, we have ya squared on the left and ya squared on the right. So let's rewrite this entire expression now. So we are left with negative 2 xb xa minus 2 yb ya equals, so we have only this term now, so negative 2, the square root of xa squared plus ya squared multiplied by the square root of xb squared plus yb squared multiplied by cosine theta. You probably noticed that we have a negative standing out here in front of every single term, which means it's a common factor. And we'll take out the common factor because why not? So on the left side, we'll have negative 2. And another thing I want to do is just rearrange xb times xa. These are numbers, so I'm going to write xa, xb minus ya, yb equals the left side. Nothing changes here, so let's keep on copying and pasting it for now, obviously. So simplify the negative 2 from both sides. So that is gone. And as you can see now, we ended up with some square root terms on the right side and these two terms on the other side. So what we're going to do next is think, can we bring them together? Or what do these represent, first of all? So, and what does this side represent? So xa, xb minus ya, yb, by the way, plus ya, yb, my bad here, would represent actually the dot product of two vectors in algebraic form. And which vector would that be? Well, let's think about it. That would be the vector, or the vectors OA and OB. Remember that OA is XA, YA multiplied by XB, YB. If you multiply these two vectors together, we multiply the x's together and the y's together. So OA times OB would be XA, XB plus YA, YB. So what that means is that the left side of the equation, basically, the side of the equation, is the product OA times OB. Now, on the right side, we have the square root of xa squared plus ya squared. That would be the magnitude of vector A. Then we have root of xb squared plus yb squared. That's the magnitude of vector B. And then cosine theta. So voila. This is the dot product, which states that two algebraic vectors multiplied will be the product or represent the product of magnitude of A, magnitude of B, cosine theta. And this is a proof for it. And I hope that you found this useful, and I hope you found this interesting to observe and to think about, and keep loving proofs. They are very important in developing a confidence in formulas, in what we learn in mathematics in general. All right, thank you for learning with me. Bye for now.